All right, this video is going to be a follow-up, going over some examples using what we learned last video about vector algebra and Newton's second law in Cartesian and polar coordinates. Okay, I have the problem set up as let U be an arbitrary fixed unit vector and show that any vector B satisfies B squared equals U dot B squared plus U cross B squared. This is not too hard of a problem, and yet it shows quite an interesting result. So first writing U dot B, this is going to be equal to the length of that vector A times the length of the vector B cosine theta, where theta is the angle between A and B. I guess this isn't A and B, this is U and B. Pardon me. Now it says that U is a unit vector. So a unit vector is going to have a length of 1. So U dot B is going to go to just the length of B cosine theta. And now evaluating U cross B, all right, this is going to be equal to the length of U times the length of B times the sine of the angle between them. Again, U is just a length of 1 because it's a unit vector. So this goes to length of B sine theta. Now, visually, what this looks like, and this, I think, is the interesting part. If we have a unit vector called this guy U, and then we have another vector B. Here we go. The U dot B term is simply going to be the term that is the amount of B inside U. So I think first it'd be worth it to draw out the U cross B term. And that is going to be the line perpendicular from the tip of B down to the vector U. Ooh, that's not quite perpendicular. There we go. And this length here is U dot B, the amount of U that is in B. And this line here is U cross B. And that is the amount of U that is perpendicular to B. The amount of B that is perpendicular to U. Sorry. And notice here what this is saying is we had from above B squared equal to U dot R, U dot B squared plus U cross B squared, right? U dot B is just this length down here, right? And if we call U dot B, if we call that A, then we have B squared is equal to A squared. And if we say U cross B is equal to, say, C, then we have B squared equals A squared plus C squared, which is just going to be the Pythagorean theorem. Quite an interesting result. Okay. The second question in this is a bit of a longer, more in-depth question about Newton's second laws. The question is, a ball is thrown with initial speed v0 up an inclined plane. The plane is inclined with an angle phi above the horizontal, and the ball's initial velocity is at an angle theta above the plane. Write down Newton's second law and find the ball's position as a function of time. Show the ball lands at a distance r equals v naught squared sine theta cosine, all this from its launch point. Show that for a given v naught and phi, the maximum possible range of an inclined plane is this. Okay, I've gone ahead and already drawn what this is going to look like. And this is assuming the axes I've drawn in blue, where z axis is across the plane, x axis goes up the plane, and the y axis is normal to the plane. The first thing we should do is draw a picture and find force of gravity in the x and y direction. So if we start with gravity, say this is the ball, it's going to pull down with Fg. There's going to be some amount, I can draw that, some amount in this direction, which is going to be y, some amount in this direction, which is going to be x. So this is going to be Fgy, this is going to be Fgx. I think it's worth to also draw a second picture that is going to be of the ball with its velocity. So if this is the ball's initial, okay, that sucks. Here we go. If this is the ball's initial velocity, this is going to be the angle phi, I forgot to mention that. And then we have a component this way. Well, sorry, it'll be more so like this, the x and the y. Just trying to follow the axes. Not the best drawing, but this angle will be the angle theta that it is thrown at, so which makes this v naught cosine theta, makes this v naught sine theta, and then that'll be equivalent for the Fgy and Fgx. If we write those here, Fgx, that's going to be equal to mrx double dot, which is going to be equal to negative mg, force of gravity, sine of phi. I think we should move this over, do Fgx on the left side, we'll do Fgy on the right side. Fgy equal to mr double dot, y direction. This is equal to negative mg cosine phi. Okay, so this is d squared x dt squared, I can write that better, dt squared equal to negative mg sine of phi. Integrate, we get dx dt equal to negative gt sine phi plus v naught cosine theta. Probably gonna need to make some room for this when we do Fgy. Integrate again to get x of t. We're integrating with respect to t here. And this is going to be 1/2 gt squared sine phi, plus v naught t cos theta. Cool. And then we have in the y direction, it'll be the exact same steps and essentially the same result. dt negative g cos phi dy dt equal to negative gt cos phi plus v naught sine theta, y of t equal to negative 1/2 gt squared cos phi plus v naught t sine theta. Cool. Box these. These are the positions. Okay. Now, what we can do is to find its max distance. So, max distance. If you imagine if we're throwing the ball, if we start down here, and we throw the ball and it goes up, its max distance that it travels in the x direction is going to be when y is 0, right? So max distance at y equals 0, so we do y of t equal to 0, so that's going to be negative 1/2 gt squared cosine phi plus v naught t sine theta. Okay, we move the 1/2 over, 1/2 gt squared cos phi, that's equal to v naught t sine theta. Divide out a t, 1/2 gt cos phi equal to v naught sine theta. Solve for t. T is going to be equal to, so you just divide over that gt, so you have v naught sine theta, 2 v naught, divide over the 1/2, you get 2. 1/2 cosine phi. This is going to be important, so let's box that. There we go. And we are going to want to substitute this into our equation for x. Because remember, when we're at our max distance in the x direction, that's when y is 0. So we have the time when y is 0. Now we substitute this in for our equation for x to find the max distance in the x direction. That is going to look like x of, write it out, x of t is equal to 2 v naught sine theta g cosine phi. I may not have enough room for this. 1/2 g sine phi times 2 v naught sine theta over g cos phi squared plus v naught 2 v naught sine theta over g cos phi times cosine theta, right? We just plug that in to our x equation right here. Okay. Now, this max distance, they say in the question, is r. Right, so we're going to have big R, and that's going to be equal to all of this stuff. If we square the first time term, so we have sine t, then we have 4 v naught squared sine squared theta over g squared cosine squared of phi. And then plus, and if we multiply in the v naught and the cosine, 2 v naught squared sine theta cosine theta over g cos phi. Okay, r simplifying, r is going to be equal to this term, multiplying this stuff in, negative 2 v naught squared sine phi sine squared theta over g cosine squared phi, plus, and then we are going to do this stuff that we already have, 2 v naught squared sine theta cosine theta over g cos phi. We're going to multiply this by cosine phi over cosine phi. So we're multiplying this side by 1. This is just going to give us common denominators in our 2 terms. So we can combine it into 1 term. And this is going to be kind of big. 2 v naught squared times negative sine of phi sine squared theta plus sine theta cosine theta cosine phi, and you make this bigger, and all that over the common denominator g cosine squared phi. Okay, what we have in the numerator is quite big, and we can simplify it using trig identities. So simplifying numerator. Okay, we have negative sine phi sine squared theta plus sine theta cos phi. If we pull out a sine theta out of this first term, the whole thing, sine theta, and this is going to be multiplied by negative sine phi sine theta, and then we pull out the sine theta out here, so this leaves us with cosine theta cosine phi. And now this needs a parenthesis. This big term here can simplify. We keep the sine theta out front, and we get sine theta. This negative sine phi sine theta can go to cosine theta cosine phi minus sine theta sine phi. And then from a trig identity, this just goes to this big term in the parentheses, just goes to cosine theta plus phi. All right, cool. Now we've simplified the numerator as far as we can go and into something a lot more readable. So plugging that back into our numerator gives us r equal to 2 v naught squared sine theta cosine theta plus phi all over g cosine squared phi. And if you remember up top in the question, this is what we were trying to show. And this is indeed what we have down below. Great. So we have shown the max distance. Now we want to show for a given v naught and phi, the maximum possible range up an incline is that R max. Okay, to find R max, let's see, finding R max. What we want to do is take dr d phi and set that equal to 0, and then solve for theta. Okay, why are we doing that? Well, it's not intuitive at first, but if you imagine a graph where you have r as a function of theta, right? The max distance, or the distance it travels r, is dependent on the initial launch angle theta, right? And if you have no angle, it'll go some distance. I guess it'll go zero distance if you have no angle. And then at some angle, it reaches a max distance, and then everything else is down below, smaller than that max distance. And so we want to take that derivative when the derivative is 0, which is going to give us the maximum distance for theta. And then we want to plug that in for r. That'll give us an equation only dependent on phi. All right, so doing dr d theta equals 0. That's going to be dd theta of our equation for r, which was 2 v naught squared sine theta cosine theta plus phi over g cosine squared phi. Okay, and so then we're going to have 0. We can pull out constants, 2 v naught squared over g cosine squared phi dd theta sine theta cosine theta plus phi. And this is going to give 0 equal to 2 v naught squared g cosine squared phi multiplied by, okay, sine's going to go to cosine theta plus phi, and cosine goes to negative sine theta plus phi. Okay, and then we can expand these. I know before we use trig identities to simplify these, well, now we are going to use that same trig identity to expand this. We still have the 2 v naught squared g cosine squared phi out front. And that is going to be multiplied by cosine theta plus phi plus cosine theta minus theta plus phi over 2. I may run out of room over here. Write this concise cosine, and this will be theta plus phi minus cosine of theta plus phi over 2, just barely. And then all of this is going to compress down nicely to 2 v naught squared g cos squared phi times 2 cosine 2 theta plus phi. Okay, now we need to find what theta is. All right, so this term is 0 in cosine of 2 theta plus phi. Our cosine to both sides. Our cos of 0, our cosine of cosine gets rid of that. So then we have just 2 theta plus phi. Our cosine of 0 is pi over 2. 2 theta plus phi. So then we have theta is going to be equal to 1/4 pi minus 2 phi. There I've subtracted over the phi divided by 2. Pulled out the 1/4 from the pi. And then multiply the phi by 2. That gets us the 1/2 phi. Okay, so now we know what theta is. And so now we can plug this in to find R max. R max is going to be, I can draw that better, 2 V naught squared sine, and then we have pi over 4 minus phi over 2 cosine pi over 4 minus phi over 2 plus phi over g cosine squared phi R max. Simplify this a little bit. We still have 2 V naught squared sine of pi over 4 minus phi over 2 multiplied by cosine, still pi over 4. But now we have plus phi over 2. And this all over g cosine squared phi still. Okay, we are almost there. This is going to get pretty messy, but it is going to simplify nicely to what we want. We are going to use some trig identities to expand this. We're going to have R max equal to, and this is going to get really, really big. We'll have 2 V naught squared. Multiplying everything, we'll have sine pi over 4 cosine phi over 2 minus cosine pi over 4 sine phi over 2 times cosine pi over 4 cosine phi over 2 minus sine pi over 4 sine phi over 2. Look at that. Just enough room. All over still g cosine squared phi. This expansion was done all using trig identities. We've used quite a lot, so good practice for our trig identities. And then R max, this is going to simplify. Maybe to about this size. We will have V naught squared times 2 V naught squared times, and this is going to be divided by root 2. This goes to cosine phi over 2 minus sine of phi over 2 multiplied by something very similar, divided by root 2. We have cosine phi over 2 minus sine phi over 2. And then, of course, g cosine squared phi in the new denominator. Okay. Now we can multiply this through. There we go. This will give v naught squared. All right. Root 2 times root 2 is just going to be 2. I'm just going to cancel out with the 2 we have out front with the v naught. Still multiplying everything, this will be cosine squared phi over 2 plus sine squared phi over 2 minus 2 cosine phi over 2 sine phi over 2. Okay, this now goes to, we have a cosine squared plus sine squared, everybody's favorite trig identity, going to 1. So v naught squared, we'll have 1 minus 2 cosine phi over 2 sine phi over 2 g cosine squared phi. All right. Simplifying some more, v naught squared, this goes to 1 minus sine of phi. How nice is that? And to get, what is our solution up top? All right, we're looking for v naught squared by itself divided by g plus times 1 plus sine phi. What do we have now? This is perfect. So now what we can do, we're going to have, where is it? Come on, there we go. V naught squared 1 minus sine of phi over g cosine squared of phi. And we're going to multiply that by we're going to change the denominator. This cosine squared, finally we changed the denominator. Cosine squared is equal to 1 minus sine squared and now we multiply the top and bottom by 1 plus sine phi okay, we have R max equal to v naught squared 1 minus sine squared of phi g times 1 minus sine squared of phi times 1 plus sine of phi. And then this is going to very nicely go to, that's crooked, v naught squared g times 1 plus sine of phi. And that is our final answer. R max possible range up inclined plane is v naught squared over g times 1 plus sine phi. And that is indeed what we have here. Perfect.